Hello, everyone, and welcome back to JNation 2020. Hope you are all doing fine and having a great time with us. In this session today, we will have with us Sendil Kumar that will be presenting us web WebAssembly for the masses. Hello, Kandil, everything fine with you?
Yeah, it's good. How are you?
I'm fine. Also, a little bit tired because lots of sessions today, but all is fine and running good. So, are you ready to rock this session?
Let's do it then. Awesome.
Okay, so without further delays, I will hand it over to you. And big thank you for being with us and sharing some knowledge.
Thanks a lot for that. Cool. Hello, J Nation. How are you doing today? Hope everything is going good. So welcome to the session, WebAssembly for the Masses. I'm Sendil, and I'm basically from southern part of India, and I'm currently living in the Netherlands. And I'm a developer, and I'm also part of an open source organization called as JHipster. Have you heard us about? It's a full stack application generator. So what we're going to see today, so we will first start with what is WebAssembly, and then we will move forward. What are the things that is running under the hood and what you need to know when you're running WebAssembly-based application, and what are the multiple languages that we support, and what are the things to know before you venture into the WebAssembly journey. So let's get started. What is WebAssembly? So just before we see what is WebAssembly, let's go a little bit back, see how this entire ISA and things like that work. So you have a computer machine server, anything, and this piece of machine works only with binary code, which is zeros and ones, right? And you cannot type those zeros and ones to run any algorithm or any program that you want to do. It's just much more difficult and complex. It's not impossible, but it's very difficult to maintain. So what we initially did, we created an abstraction layer. And we call this abstraction layer as an assembler. And the job of assembler is that you just do the code, like outputs or an assembly code. And this assembly code is converted into binary, and that runs on the machine. Right. But it's not maintainable. It's not human readable. It's not very easy for us to understand and formulate an idea around it. So we have another layer of abstraction on top of it, which we call this high-level programs. And this is something that you just give something in a human readable format and then convert this into compiler and then run this entire thing. Right. So this is how it works. But the end machine or system or server, whatever you see it over there, is complex, right? So we have different operating system, different ISAs, and which makes it very complex for us to run things. So this compiler or this assembler has to segregate or generate a binary code that's compatible to run in multiple different ecosystems. And this is a major problem. And this actually hinders our software distribution, which means like you create an application and then you have to distribute in the world. You cannot do it much more easily because you have to make sure that the particular environment in which it's running, there are certain softwares or runtimes that are installed with which you can run whatever you need to run. And this makes it much more complex. So browsers came into the land and web actually came into the land, and that kind of solved a lot of problems. So you need not think about distributing it to different environment. Browsers came here and then said like, okay, so think I am there always, and then try to build something for me. So it said like, okay, give me the code, I'll run it on any server or any machine. Cool, that's a really good thing, right? So you can run those things anywhere. Like it will understand only HTML, JavaScript, and CSS, which is it's really, really difficult to do it. It is easy on one level because the language is much more easier. But the problem is like it just accepts one single set. And you have to make sure that you're running or creating everything based on that. And that makes it much more complex, right? But under the hood, browsers had a JavaScript engine, a GPU processor, a layout processor. And the layout processing is essentially for CSS stuff, and JS engine for JavaScript stuff, and then the GPU processor for any extra work that is needed. And that made it much more easier. You just put in your HTML, JavaScript, and CSS, and kind of converts everything that you want to have. And then you added a WebAssembly module. You added a WebAssembly module here, and the WebAssembly module actually runs the WebAssembly engine, which is running there, and that kind of helps you run the entire application inside the browser. So what is a WebAssembly as a whole? WebAssembly is a stack machine that is designed and encoded to run in size and load binary. Format binary, and WebAssembly aims to have a native state by taking advantage of common hardware technology. Ricardo? So that's what is happening. And so you have your native code, you just convert that native code into binary code and then optimize them, and then you have an optimized code. And that this optimized binary code is what you have at the left-hand side, and then you have to run this inside your browser or JavaScript engine. And you have this JavaScript engine, but JavaScript engine does not understand the binary code that you're sending it. So you need to have some mechanism to make it understand, and that's where the WebAssembly engine comes into picture. The main thing for WebAssembly engine is like it interprets the code that you're sending, compile them, and then run it. And yeah, so but every time when WebAssembly has to call something in the JavaScript, it has to cross over the boundary between them. So there is a boundary that lies between the different engines, which is WebAssembly engine and JavaScript engine. And so now you just send your binary code inside, the WebAssembly engine will interrupt and compile and then run this binary code. And then this will in turn talk with the JavaScript and then execute. But why do we need something like this? Why do we need something like WebAssembly? Why cannot we do with JavaScript itself? Because JavaScript is omnipresent, right? So you have multiple different set of things. JavaScript is you can write devices, you can run server notification, all those things.
Ardorzinho assim, fresco, tá vendo?
All those things, right? So, but the main problem with the JavaScript stuff is like it is unpredictable. I hope everybody has seen something like this when you're working on Internet Explorer. Some errors like this, and also this one. And finally, you also have something like WebAssembly, which is like you cannot. This entire thing is unpredictable and not maintainable. The entire stuff that you're having is unpredictable and it's not maintainable. And also JavaScript as a language is weird. It has some weird corners. Every language has weird corners, and similarly JavaScript has some set of weird corners. And for example, this entire code segment will evaluate right? And the most important thing is type, which means like you have a type information, like you cannot have anything typed here. So this it's a string at the first, and then it turns into an array, and then to object, and then to number. So you can convert this kind of text in JavaScript, and it's dynamically typed, of course. But the main problem is like in the world of TypeScript, you can have something like TypeScript that helps you to create the types and then run it. But underlying the entire system is not built for having types. So of course your code is converted into JavaScript and runs without any types inside. And that is the problem. You're trying to fix something at a compile time, but you will not be sure what on the runtime inside. So that is a major problem that you have. So WebAssembly comes into the picture here. So it kind of helps you to do that. So WebAssembly is typed, which means that you can everything that lives or runs inside the WebAssembly execution engine is completely typed. And currently, we just support like numbers, which is I32, I64, F32, F64. And that is the most important thing. So you have types that is built inside the compiler as well as when you're writing the code. That is very important. And WebAssembly is fast. It gives you a near native performance. It is more faster than the JavaScript. But the problem is like when WebAssembly and JavaScript works together, it has to cross this boundary together. So when you're creating an application, you have to think in that terms like, okay, so I should not call multiple times any code that kind of calls or crosses the boundary again and again. And that is very important. And finally, it's very important to know WebAssembly is not always faster. The WebAssembly is faster only at certain solution, but not every time. So for example, if you have an application that runs with DOM, that needs to access DOM a lot of time, I would say WebAssembly is much slower in that side than compared with the normal application. On the other hand, WebAssembly is secure. So it is very secure because it runs inside a sandboxed environment. So it's kind of your browser or something like that. It runs inside that environment. And it also follows a linear memory model. It also so it follows a linear memory model, and then you have this memory access, which kind of helps you to which actually implemented based on shared array buffer. And the problem with that is like it gives us scepter or meltdown issues, which is we had initially due to this execution in the Intel CPUs. But it is much more secure than whatever we had, or whatever things that we tried to run, whatever the native code that we tried to run in the browser world. So it is much more secure. WebAssembly is portable. On the other hand, it's very independent. It's independent of platform, it's independent of the operating system, and any language or platform in which you're running it. So that is the coolest thing about WebAssembly. So that is what WebAssembly is at a high level. Great. So what are the things that lives under the hood? So how does WebAssembly works inside the browser or any JavaScript engine? So let's see that. So just before seeing how WebAssembly works, we need to know how JavaScript works, right? So how does JavaScript works? So you have this JavaScript code. So what will happen here is like once you specify JavaScript code, the browser will go and fetch the entire JavaScript file from the place that you have mentioned. So it could be a CDN server, it could be a file server, or it could be anywhere. Then it downloads the complete file. It has to wait till it finishes the download of the JavaScript. So the complete file has to be there before doing any execution. So it waits. If you are on a slower network, it takes a longer time for you to download this entire file. So once you have downloaded this entire file, then what you do is like you parse this entire file and then you convert into an AST, which is abstract syntax tree. So this is just an internal format. It's just a tree kind of architecture that kind of helps you to initialize all those things. And this ASTs are what the compilers will work on. So as you know, JavaScript is an interpreted language. So what will happen is like this ASTs are converted into bytecode and then interpreted, and then it's converted into bytecode, and that bytecode executes straight away, since it's an interpreted language. But again, JavaScript is compiled language too. So what will happen? So there is, in every browser, it is called as a different name, but there is a profiler or a person who sits there. Consider him as a person who sits there and then watches how your functions are executed. And if a particular function is called multiple times, so what this guy will do is like, okay, so this function is called multiple times. Let me mark him as a hard function. And then what it'll do is like it'll try to compile that function. So instead of running interpretation every time, what it does is like it spends a little amount of time to convert this ASTs into compiled code, and then uses the compiled code and executes it. And that's what is happening. Great. So you have this compiled code, but of course the engine has to spend some time to convert this ASTs into compiled binary code. That's number one. And number two, we don't have any type information here, which means the engines has to assume certain type information here, and it has to work. So it has to have a lot of type checks to assume something is working. So if the type checks fails, then it goes back to the interpreted code. And that is the problem with the type. So if you are misusing your types, what happens here, instead of going to compiled code, the code actually goes to the interpreted way and then runs, which takes a longer time to complete, and it's also not very efficient. And that is a major problem with respect to types in JavaScript world. Okay, so you have this compiled version of the code, and then it executes. But JavaScript also has this notation of optimization in the code. So optimizing the code that is generated. So the engines are built for performance and fastness. So what it does is like, instead of just running the compiled version, which is giving high performance, it tries to optimize the entire code. And this optimization, what actually it does is like it adds on more assumptions on top of what it has assumed before. So it adds a lot of assumptions like, okay, this is string for a lot of time, so it should be a string. This kind of assumptions are made, and the compiler, the optimized code is much concise, and it sounds very fast than compared to the other two versions, of course. But the browser spends a little bit of time in converting those optimized code. So you literally spend some nanoseconds or some second, which are like performance high stuff, when the execution is happening, again, to iterate. So it doesn't have any type information here. All those things are assumed. So once this entire thing is done, it is executed, and finally everything is garbage collected as a whole. So this is how a JavaScript works. JavaScript works inside your JavaScript engine. So the file, it has to wait for a long time till everything is downloaded. It parses it, and then it tries to interpret and run it. It marks certain functions, hot function, and then compiles it and run it and executes it. And then it does an optimization as a second level of compilation. So this is how it works. On the other hand, in the world of WebAssembly, so this is how you load a WebAssembly. It's again loaded with the help of JavaScript. So you first fetch the WebAssembly module. This is literally from any server or anywhere. And then what you do is like you convert that response into an array buffer. So you use that array buffer and then compile this entire thing using WebAssembly.compile. Once it's compiled, you instance it or instantiate it. And once you have instantiated, you can use that as a normal JavaScript object and a function call inside your JavaScript code. So that's basically it. So it's literally you fetch something from somewhere, you convert that into an array buffer, and then you compile and instantiate that thing. So this is a binary code, WebAssembly, as I said. It's just a native binary code. So this binary code is there, and it's encoded for security reasons. So you just decode it. So once it is decoded, it is compiled, and then finally it is executed. That's it. So the process of running a WebAssembly module inside your browser or a Node.js or JavaScript engine is much simpler. The decoding part is much faster, and compile here you're compiling an already compiled and optimized code, which means it's much more faster and much more optimized to run. And then you finally execute this entire stuff, and that is the normal time that it takes to do any function that you wanted to do. So the decoding is much more faster, and here the engine does not have to wait till it gets all the bytecode from the system. So it need not have to wait till everything is downloaded. As and when the bytes are coming, it just converts, compiles them, it just decodes them and compiles them, and it's ready for execution. And that is a major benefit that you get. And second thing is like everything that runs inside here is typed. And that gives enormous flexibility for the compilers to optimize any level that it wants to do. And that is the major feature with respect to WebAssembly that helps you to do a lot of stuff much more easier. So that is basically what is WebAssembly and how it works under the hood. So the next obvious question is like, okay, cool, it looks really great. So what can I do with it now? At this moment, you can have certain set of languages which can be converted into WebAssembly code, and then it can be run on your browser or a JavaScript engine. So you have your native code, you convert that native code into a binary code, and then that runs inside a WebAssembly engine. And then you have this native code. This WebAssembly code cannot run inside your JavaScript engine, of course, and you cannot run this entire thing without a binding file. The reason for the binding file is like because WebAssembly currently only transfer numbers between WebAssembly and JavaScript. So you need some kind of a translator to sit between the WebAssembly engine as well as the JavaScript engine and sit between those things and then converts anything that comes into it. So for example, if you want to send a string, this binding file generates all the binding that is required. What it will do is like, it will just take the numbers that is coming from the WASM side, and then it converts that into a string, and that goes into the JavaScript world. And in the JavaScript world, if you want to return a string to the WebAssembly world, so this binding file actually sits between the JavaScript file. So JavaScript file sends a string, and this sends a string to the WebAssembly as a number, and then it uses this thing. But sending number here and there might be much more complex, right? So what it does is like, it just uses a shared array buffer between these two, as we seen before. It just uses a shared array buffer. And this shared array buffer is responsible for putting all those things into memory. And next time, if you just want to send a string, you just need to have a starting of the pointer and the length of the string that you want to send. And then anyone, like for example, WebAssembly engine can use that information to fetch the entire string, or the JavaScript engine can use that to fetch the entire string. So this entire thing is called as WASM toolchain. And this toolchain is responsible for converting as a native code into a WebAssembly module, as well as creating the binding file that is required. Cool. So the first and foremost, we have C and C++ that is supported. So in the world of C and C++, the thing that converts the native code into binary code is called as mscripton. So mscripton is a tool that helps you to convert your native code into binary code. Actually, in the world of C++, C and C++, you have this LLVM. So what it does is like it takes, it it generates an LLVM bytecode, and then it kind of creates a native code that is compatible to run in the WebAssembly agent. So that's basically it. And then you have something called as mbind. Mbind is actually a tool that helps you to create this binding file for the native code that you have written. So these two will help you to generate a WebAssembly module that is created from C and C++. So how you do it? So it's a tool that is available in GitHub. You can just get that repo, build it, and then install and use the latest version. And that's it. So you will have this emcc command, which is the scripting compiler. And this is a simple hello world program in C. So basically, you don't have to do anything. You just have to include this mscripten.hatch header, which kind of helps you to generate all the auto-generated stuff that is required for running a WebAssembly stuff or generating the WebAssembly module. And finally, you just run emcc, given the hello.c, which is the file name, convert that into WASM, and the output as hello.html. So here, you're actually creating an HTML. And this HTML will create all the environment, all the binding file, all the binding JavaScript, and the WebAssembly module. It couples all of them together, and you just have to run this HTML, which kind of generates or prints out the hello world as expected. On the other hand, if you go a bit higher level, I mean, like if you want to share a function between C and JavaScript, what you can do is like you can just define a function. You can use the mscripten namespace again. And then you specify the separate block. This block is like mscripten bindings. Put down some module name and then give a function. So then you can generate an output JavaScript. And this JavaScript output is actually a function that is generated. This is a binding function that kind of helps you to convert anything that you're giving here. So that's a binding file that is generated for you. And there will be a WebAssembly module that is also generated. So if you go to the next level, which is like sharing a classes between your JavaScript, between your JavaScript and C and C++. So you can define a class, you can put some implementation, and then you again define an mscripten binding block, and then you define a class, a constructor, a list of functions that you want to export, list of properties that you want to export, and all those things. As you can see, it's like C and C++. It is kind of like very verbose, and that is the major drawback with rest of C and C++, because you have to go and define everything that you want individually to export it. And that is the major drawback. But the major advantage of using C and C++ is like it's based on mscripten toolchain, which is on top of which all other toolchains are built. So it is the base and first and foremost toolchain that is built for WebAssembly, and it has all the cool and new features available very early. And it is useful for having a very good performance. So C and C++, of course, it's known for its performance. So it also gives higher performance. The code that is generated is optimized at a very high level than compared to any other thing that you have. On the other hand, it is verbose, as you can see, like a simple point class. It takes a lot of things that you have to define, and then you have to write a separate block, and that tells the compiler how to generate the binding file and all those things. So it is very verbose, and if you're trying to change whatever you have at this moment, so for example, we have a C and C++ image encoding library, and you want to convert that into WebAssembly module, you have to write a lot of things that makes it really, really verbose. And of course, it's C and C++, right? You have to take care of dangling pointers and all those things. On the other hand, in the world of Rust, so Rust is a new programming language. It's a system programming language, which is built for safety and no dangling pointer errors. So here in this world, you have this native to binary code converter inbuilt into the compiler. So Rust basically have first-class WebAssembly support, which means like if you have installed a Rust compiler in your machine, the Rust compiler is capable of generating the WebAssembly module. And that is really awesome because it's built into the compiler. And on the other hand, to generate the binding file, we have something called as WASM binding generator, which is WASM bindgen, which is a cargo module. You can install this thing. You can install it and use it. So it creates a binding file that is required for you. So how do you do it in the Rust world? It's very simple. You define a function. For example, this is Fibonacci series, which is a classic example that is used in WebAssembly world. It just takes in a number and then converts it to a number. It's a recursive function. And then you specify this hash nomangle as an annotation. And what it does is like now the compiler knows that this entire thing has to be built for WebAssembly by giving this target WASM32 unknown. So it basically understood, okay, so this is WASM32 unknown, and generating a target for that, and building my native code for that target, and then it creates all those binaries for you. I mean, the WebAssembly module for you. And then you just use this WebAssembly module that is generated, and just do the same set of thing. You wait for the array buffer, you instantiate it, and then you just call a Fibonacci on top of it. So it runs a function, it runs the WebAssembly code, and then returns a number, and it prints it over here. But what if you have to do a more complex object, like passing a class from the Rust world into JavaScript world? So you can use a WASM engine. So you have to import the WASM engine library, of course. And then you can use this annotation, hash WASM engine, over the struct and also the implementation. So what it does is like it generates all the necessary binding automatically. So you don't have to deal with the verbose that you want to add in here. So you just do cargo build, and then you call WASM engine target, go to the point.wasm, and then generate it in your local directory. So what it does is like it creates a binding file, and then it optimizes the WebAssembly module also. So WASM binding is a tool that kind of helps you to generate the binding file, right? So it kind of helps you to do that entire thing, and then you have this JavaScript binding file and a WebAssembly module generated. So in the world of Rust, everything is inbuilt to the compiler. That's a huge advantage that you get. And it has a very good toolchain available, and it's the best that is available at this moment. But sometimes it creates a bloated binary, and all we are trying to deal is like optimize the binary that is getting created. So it creates a bloated binary. Performance, it's slightly tad lower than C and C++. It could be better at some places, but at the most of the places, it's kind of having a little lower performance than compared with C and C++, because behind the scenes, it again uses the mscripting and all those things. So this is something that you have to take into consideration. And I've also written a series of blog posts on Rust and WebAssembly. If you're interested into venturing what to do with various tools that are available, I'll just share the slides after this presentation. You can use the slides to go and see how Rust and WebAssembly, how to use Rust and WebAssembly in much more detail. And then you have something called as assembly script. So assembly script is something like a superset of TypeScript. So what is assembly script is like, it's a language that is built exactly similar to TypeScript. It's heavily typed, and use that typed language and then convert that into WebAssembly and then run it on the browsers. So in the world of, it's much closer to JavaScript ecosystem, which means like it's much more similar. What you're seeing is, it looks like a normal JavaScript function, right? So it's a Fibonacci again. So here you run through the numbers, it's an iterative version, but you run through the numbers, you generate the Fibonacci, and then you return the value of Fibonacci. That's basically it. You have something called assembly script compiler, and then you just generate the file, and then you optimize it to the maximum level, just O3, which is much more similar, right? Smaller, simpler, right? And it lives as an NPM node package. So they're just like, this is what I said, like it's much closer for any JavaScript developers to get into WebAssembly. And it's typically, if you take a look at it, it's kind of a TypeScript, but it's not TypeScript. You just have to initialize everything. You just run this loader, you just run this assembly script, and then you can build your application much more faster with it. So on this note, assembly script is very, very fast than compared with whatever we have seen so far. It's very much optimized, and it's much closer to the front-end world. It is closer to the JavaScript ecosystem, but it is not TypeScript. It kind of looks like TypeScript, but it is not TypeScript. Toolchain is not very complete, and that is a major drawback that we have. It's not very complete, but we do have a very good toolchain support. And of course, you have something like TinyGo or Go. So you can convert your Golang into WebAssembly binaries. There is Kotlin native, and then there are Surf Java, Erlang, and others, which are still in like early years of converting your JavaScript into, your native code into WebAssembly. But it's still early. But Go has a very good support, especially the TinyGo. It produces enormously tiny binaries, and which is like more than 70 to 80% smaller than the normal Go binaries. And that is really, really efficient, whatever you're seeing there. So just before going to the next part, let's go and have a look at the demo. So this is one of the example of game of life. So let's see what it is doing. So let me just go and start it. So it is running. As you can see, it's like much more faster. So here you can see like we have more than 90K of small particles that are running around, and it's much more smoother. And the refresh rate is happening for every 30 seconds. And as you can see, it's very super. You don't see any lagginess here. So if I try to run this thing, so you don't see any lagginess here. It kind of creates a lot of smaller particles here. It's game of life, typical game of life. But it kind of creates a lot of tiny particles, and then it runs entirely inside a canvas. But as you can see here, it's giving a much higher performance. And also, you can see it's much more robust. You don't see the lagginess. You don't see, stop script errors and things like that. And that is what WebAssembly is here to provide. So to provide this kind of stuff. So let's go back to the code. So what is it's a normal npm file. That's a npm package. So as you can see here, this is actually taken from Game of Life example that is available in assembly script library. And it has nothing. It just had two dependencies. One is the assembly script and a HTTP server to run the server. So assembly script is what actually does the magic for us. So as you can see, this is again a TypeScript file. So it is kind of like TypeScript, but it's noted as TypeScript file. So here you have this config, which kind of declares all the major constants that we're going to use, or major types that we are going to use. And then you have this index.ts. Here you can see that inline function. This what it does is it gets loads the value from the memory that is shared, and then it goes and stores a value inside a memory. And yeah, that's basically it. And the init function is called at first. So this is a function that is called from JavaScript world. And what it does is it sets an height and width of the platform. So for example, if I shrink it, it's not responsive, but if I shrink it, so if I shrink it and refresh it, so now you can see it's much more polluted. So the init actually takes care of height and width based on the rectangle size, and then uses it, and then it fills out all those things. It fills out the live thing, and then it fills out the dead, right? So dead is something like if 3 pixels around it is dead, then the inside pixel is considered to be dead. So that's how. And then it calls a set function. So set function actually stores everything, and then get function actually loads everything into the picture. And then you have the step. So this is performs one step. So this is called 30 times per second from JavaScript. So this is the frequency that you're seeing. So every time this function is called, this kind of creates, sets a set of bunch of cells to dead, and then it sets a bunch of cells to alive, and then it kind of calls it repeatedly. And even then, it's not laggy. It's running at high performance. And it kind of creates a universe that is required. It kind of sets a live cell, checks whether a dead cell is there, and does this thing. So the major tricky thing here is these two functions. So it kind of loads everything from the memory, and it kind of stores everything into the shared memory. And the JavaScript world actually uses this memory to paint everything. So if you take a look at the JavaScript world, you have nothing but a single index.html, and then it defined a canvas here, and then you define a set of configuration here, and then you create this canvas, and then you create this entire canvas, put it to a variable, and use that entire thing. So using the width and height, it calls the init function over here. So it initializes a memory object for the WebAssembly. It fetches the WebAssembly file, and then it creates an array buffer. It's instantiated here. When instantiating, it also sends in memory. So you're actually telling, oh, hey, WebAssembly, just load this file that is I'm fetching from this location, convert this into array buffer, just load this guy, and also add this memory into that stuff. So memory is actually the byte size that we are requesting. So it creates a shared array buffer and uses the shared array buffer between JavaScript and WebAssembly. And then it calls on the module. Here it calls on the export stuff, and then so this is actually where the entire bundle is chunked, and then this entire chunked bundle is given to exports. So the exports is a JavaScript object in which you can call any function that is exported from the world of WebAssembly. So in our case, we are exporting a function called as init. So it just calls the init, sets the width and height, and then it creates another array. So this is the array to read the object from and also to write the object. So this array is created, and then this update function is called every 30 seconds. So as you can see here, every 30 seconds, this function is called, and the memory copy happens inside. So it copies the memory from the shared array, and then the WebAssembly module will go and write the shared array with a new set of dead and alive cells, and then which is called back again in the update callback. So, and then you have this image data. It creates an image data, it syncs everything out, and then it renders it. So here, what we do is like, we just request animation frame, which is like just setting a 15 millisecond extra, 15 or 16 millisecond extra, and then you put the image data, and then you run this entire thing. So the feature that I've shown you, so when I click here somewhere, when I click and run this, the entire thing, it kind of creates it. So this is the feature for that. So whenever mouse up or mouse down, mouse move, everything happens for everything. Just create a bounding rectangle and then create extra alive and dead cells for you. That's basically what is happening. And that's it. So catch any errors. And there is a small function that kind of converts RGB to BGR color. And that's basically it. So as you can see, it's very small. It's very, very simple to do it. So if we go back to the code, so the entire thing is built inside here. So if you take a look at it, so what it does is like, this is the optimized WASM, which is like 891 bytes. And that is the size efficient that we're talking about. It depends on the language that you're using. For example, if it's a Rust, the game of life is like somewhere around some 100 or 100 to 200 kilobytes or something around that range. And then here, it's like just 891 bytes. And that is the size efficient stuff. And then you have something like optimized D.TS. So this is actually something that you can use for the TypeScript word. So here you're saying like, okay, so fine, these are the supported types that I have, and these are the functions that I'm exporting from it. So as you can see, just numbers, I just have numbers, and there is no relative variant of 64i and 64u in the world of JavaScript. So it just uses Bigint here. And then if you want to use 64-bit stuff, then you have to use Bigint, which is another thing that you have to take into consideration. And these are the three functions that I exported: the init function, the step, and fill. And that's basically it. So it's much more smaller, much more easier. And then you have this wasm.map, and the whole function of wasm.map is to have this debugging module ready and use that debugging module for anything that you want to do. And there is something called as optimized WAT, which is a readable format. And this is another place where you can check whether the code is right or something. This is much closer to the compiled version of the code, but it is in a readable format. This looks like a Lisp syntax. It's called as S expression, and it does all those things. So basically, it's a stack machine, as I said, right? So it takes a value from a local and then sets it to global, and then it kind of does this algorithm. Like, for example, it gets 2 value, and then does a multiplication. So it pushes 2 value in a stack, and then it pops 2 value out and does a multiplication. That is what's happening. It has a for loop and all those things. So this is what we call as bot, which is WebAssembly text format. So that's basically it. So as you can see here, the actual untouched file, which is not the optimized version, is 1.3 kilobytes. And it is optimized further to 891 kilobytes. That's basically using the -3 optimization. So yeah, that is something to note. You can optimize it just like your native code. So in your native code, you do like optimization 1, 2, 3. You can do the same kind of optimization here to increase the optimize or to decrease the byte worth that you're generating. Let me go back to the slides. So what are the things that you have to consider before moving into the world of WebAssembly? So when to use it? Use it for any computing heavy algorithm. For example, in our case, game of life, the algorithm that is heavy is like computing whether the cell is alive or dead. If you do that in JavaScript, you might not get the same performance for that many amount of live cells and dead cells. But in the world of WebAssembly, it is much more useful. So use something for computing heavy algorithm that you have. You can use it for games if you have some games that you want to serve to customers and that runs on the browser world. Use it for games. Use it for anything that is useful for WebGL. So if you are using WebGL at any point of time, the languages like Rust gives a good support for writing WebGL in a much more type constrained way than normal WebGL, which depends on WebIDL. So it is easier to write. It's kind of verbose, but it's much more easier, and you can have a complete type check and safety stuff that is provided by Rust, and that is really good to have. And another important thing to note is like if you're writing WebGL, it's better to write it in WebGL itself. But if you want that extra level of type checking, security, and all those things, then going with Rust, which kind of converts all the WebGL stuff into the binding file as and when needed. The WASM binding library has something called as WebSysCrate that kind of helps you to do it. Then any online IDEs, if you're doing some online IDEs like coding or something like that, you can use this thing. It is also useful for super fast mathematical functions. So if you already have an algorithm that kind of uses this mathematical stuff and kind of uses mathematical stuff, for example, using a C library or something, then you can just use it and port it to the web world with that. And that is much more cooler. And there are like multiple libraries that works on C and C++ because of their efficiency. For example, for the photo edition or photo masking and things like that. You can use that stuff over here. But just to understand, like when not to use WebAssembly, when your application is solely interacting with DOM and then trying to create something inside the DOM, don't even think about WebAssembly because it will not help you in that picture. It kind of increases the time and kind of like produces a lot of problem. And it's not properly garbage collected. So there is no point of garbage collection here. So which means like you have to think before using it. You can use it, but it's not advisable to use it. Your day-to-day applications, normal applications, your blogs or somewhere, it's not meaningful to use WebAssembly because it doesn't add much of any benefit there. So that is what basically you have to take into consideration before moving into the land of WebAssembly. So what is in the future? So there is a link that is attached here, which is WASM proposals that kind of shows you what are the future proposals that we have in the WebAssembly land. And it's cool to check it over there. So there are some exciting proposals that are coming, and that is kind of like helps you to write much more better WebAssembly and much more better code, much more stuff easier. So the first thing is reference type. So currently we have seen that only numbers can be passed between JavaScript and WebAssembly module. With reference type proposal, you can pass in multiple stuffs. Like for example, you can pass string or array between JavaScript and WebAssembly module. It's still in stage 3. It's not finalized. But if this proposal lands, then what you have is like you have a common interface with which like different languages like Java and JavaScript or Rust and JavaScript talk with each other. And that's really good for reference type. That's really good stuff. And then you have thread support. So currently you have threads at an operating system level. You can leverage that. The modern architectures are built with that. So you can leverage that and provide much more faster code. So there is a proposal that is happening, which is like running threads in the WebAssembly land. So you can use that. And also touching on the same feature, we have like SIMD, which is single instruction, multiple data. So this is also one of the exciting features that uses the new kind of architectures that we have, and it kind of boosts up the performance of the system. And also we have something called as garbage collection proposal. So currently WebAssembly module doesn't provide any garbage collection, which means the language in which you're writing has to take care of garbage collecting all the things that it's creating, which can be problematic, and it also causes like a lot of possible ways of creating memory exceptions. And the main problem that we are trying to solve with this proposal is like either to add garbage collection as a part of WebAssembly module, or to add as a part of like any language that is changing into WebAssembly code. So that is something that is happening. But garbage collection is also an interesting proposal, and a lot of people are talking about it. And if this comes into picture, it kind of solves a lot of problems that we have in the world of WebAssembly. And the final thing is WASI, which is WebAssembly System Interface, which is kind of like uses POSIX calls and then hooks onto your system calls and then runs whatever you want to run on your system. So it is like it's kind of like JVM you can think of. It provides you provide a runtime which is called as WASM runtime, and then try to run your application inside those runtime. You can write your application in multiple languages, and then you can put them inside WebAssembly module, and all of them run together. And that's much more awesome thing, right? So that is something which is happening, which is WASM. So you can check this out. Also, it kind of helps you to understand where we are. It's kind of like, you can think of like Node.js for WebAssembly, kind of, but it's not exactly similar. But WASM is using syscalls with POSIX, which means it's faster. And that is some exciting thing that is happening on the WebAssembly land. And that's basically it. Thank you very much. And if you have any questions, just post it. I'll try to answer them. Thank you.
All right. Thank you, Sendil. Very nice presentation. Thank you, Sendil. Very nice presentation. Very nice theme you bring us today. Here on our live chat, I don't see any questions. Let me check on the room. No. So if we have no questions, I would like to say a big thank you to you, Sendil. Thank you for being with us, and hope to see you next year. Great presentation you had us. Thank you for sharing your knowledge, and see you next year, mate.
Yep, sure. Thank you. Thank you very much. See ya. Bye.
For all the other attendees, enjoy the break. 15 minutes break. We'll see you in 15 minutes for the next section.